In this video we're going to discuss the chain rule, which was the third rule on our list. And before we start, let's look at a diagram that will help us understand the chain rule. Remember, the chain rule is concerned with the chaining together of two functions. So let's say the first function is g followed by f, and we have define some test functions just so we can do some numerical tests as we go along, but what we say applies to any functions f and g. So this is what's going on in this picture. Let's look at it. We have three number lines. The first one we'll call the x number line, the next one is the y, and then the z number line. So our function starts at x. We apply f to it and we get y or g to it. G is our first function. Sometimes we call that the inner function. We apply g to x and get y, and then we apply f to that to get z. So that's the chain of functions. Now the derivative involves varying x a little bit and seeing what that does over all the way over at the other end. In other words, we look at x plus dx, or x plus h. We're going to change our notation slightly. H and dx are the same thing here. We see what g of x plus dx is, and then finally we see what f of that is, and we just give it a different name as we go along just for the sake of convenience. Also, some of the formulas look a little more familiar. So we're defining y plus dy to be g of x plus dx, and that means dy has to be defined as where is it? Right here. Here's dy here. It's just the difference between the two g's, and we know that that goes to 0 because h is going to 0, or putting it, saying the same thing. Since h and dx are the same, since dx goes to 0, this thing goes to 0. And actually, let's just look at that. Let me start out with an h or a dx fairly large, and now dy is fairly large. But of course, if I make h smaller and smaller, dy is going to get smaller and smaller. And that's because g is continuous, and we know that as dx approaches 0, this side over here on the left, this formula here, has got to approach g of x. That's what continuity means, really. And that can be either from the top or the bottom. In other words, dx could be positive or negative. In our picture, we've sort of drawn it like it's a positive number, but we could make it a negative number also. All right, so that's our picture. And then to talk about the derivative of the chained function, that is f of g of x, we're really asking this question. How does dz compare to dx? How does the change up here compare to the change down there? And that's really just the definition of the derivative. We let the dx go to 0 and see what that does to the images up here. We divide by dx, and that's the definition of the derivative. And along the way, let's look at these two formulas here. It's pretty clear that g prime of x is dy dx, and that's just because of the way we've defined dy. Remember how we've defined dy? Let's just plug it in there. That's g. That's dy, and this is our definition of g prime of x. We'll let h go to 0, and remember, h and dx are the same here. So we have the approximate equality as being true. That's what the 1, 0, 0 means, and we can make it even a closer approximation as we make h, or using our new notation, make dx smaller and smaller. So that's the derivative of g prime at x. Dy dx, as you take the limit, is the derivative of g at x. And similarly, the derivative of f at y is this thing here. And again, it's just a definition of what is dz. dz is the difference between the f's And now dy is, this gap back here. So this picture is exactly what we're talking about when we're talking about a derivative. We look at the differences in the images. We take the difference in the domain variables, that ratio. We let the domain variables, that is dy, go to 0, and that is the definition of the derivative. So now let's actually prove our... Actually, before we do that, let's look at some examples just to get used to the idea. Then we'll get to the proof in a second. So here are some examples. And in doing these examples, or figuring out what's going on here, you should ask yourself, what's the inner function and what's the outer function? Or what's the first function and what's the second function? So the inner function in this case is g, and we call it the inner function just because it appears in, it's the most nested of the functions. It's inside all the parentheses. So to use our rule, this should be equal to, well, we take the derivative of the outer function, that is f, in our picture down on the lower right. Take the derivative of that, so the derivative of the sine is the cosine. We evaluate it at the inner function, and then we differentiate the inner function and evaluate it at x. And notice, x is back here. So this thing is chained together very nicely. We take the cosine of g of x, which is y. Y is another name for g of x. And then multiply that by g prime of x. Let's look at another. Let's look at this one. So what's the outer function? And again, you should stop the video and try these yourself, and then turn the video on and see if you got the right answer. Well, the outer function is sine. We know the derivative of the sine is the cosine. You apply that to the inner function without any changes, and then you differentiate the inner function, and that's 2 times x. And notice our 1 down here. That means we're on target. Let's look at another one. Okay, what's the inner function and outer function here? Well, what's getting applied to x first? This notation means the sine is getting applied to x, and then the whole thing is being cubed. So the outer function is the cubing function. And we know how to take the derivative of the cubing function. We take the exponent and bring it down, put it in front, and then we take the inner function and we lower the exponent to 2, and then finally we take the derivative of the inner function, which is sine in this case. So the derivative of the inner function is cosine of x, and we see our 1. So we're in good shape again. Now here's an important one. How do we do the derivative of 1 over the sine of x? Well, we're going to rewrite it and look at it as the derivative of sine of x raised to the minus 1 with respect to x. So those are the same formulas. And notice our 1 down here. We're still okay. And we know how to differentiate a minus 1 in the exponent. We just use our exponent rule. We bring the exponent down, and then we lower it. It's at minus 1, so if we lower it, it's going to be at minus 2. So another way of writing that is sine of x squared. And now we have to differentiate the inner function, which is a sine of x. So that would be, the derivative of that would be the cosine of x. And we get 99999. The reason it's not showing 1 here is because this initial derivative is calculated numerically, and it only approximates it. But this is okay. So we've moved down to this one. Let's look at this one. This was important too. Oop, we don't want that. This one here is important. It's a very simple one, but it's an important one. So what's the outer function? What's the inner function? The outer function is sine. The derivative of sine is cosine. We repeat the inner. That's plus pi over 2. And now we differentiate the inner function. Well, the inner function is x plus pi over 2. We know how to differentiate just x. That's x to the 1th power. So when we differentiate that, it's just going to be 1. And the derivative of pi over 2 is 0, since that's a constant. So we can get rid of that 1 there. That's not really adding anything. And we see our 1 down here. And so this is okay. Let's look at another. Hope you're getting the idea here. All right, what's the outer function here? Well, it's sine again. I'm using sine over and over again because it's easy to see it as the outer function. So there's nothing special about sine here. It's just that it's easy to see what's going on. So what's the derivative of the outer function? It's the cosine, and you have to repeat the inner function without any changes, plus 1. And now differentiate the inner function. And that's a polynomial. We know how to do that. That's 6 times x plus 2. And again, we get the 1, or approximately 1. So this one's okay too. And now we're going to look at another inverse, just because I want you to get used to dealing with these inverses, because it's going to be important when we go to prove the quotient rule. So how do we think of this? This is an exponent of minus 1. It's the equivalent to having 3x plus 3 raised to the minus 1 and then taking the derivative of that. So we know how to deal with a minus 1 in the exponent. We say bring it down, and then you multiply times the inner function raised to the minus 2. But I'm going to do it like this. We know that that's the same as putting it on the bottom, times x plus 3, and we want to square it because that's a minus 2. And then we want to differentiate the inner function, and that's just 3. And we get our 1, so I haven't made a mistake there. And one more time, the inverse. I'm kind of beating a dead horse here, but I want you to get comfortable with this idea. So we think of this as a minus 1 exponent. So we bring it down, divide by g of x squared, and then differentiate the inner function, and we get that as our derivative. And now finally, here's an interesting one. This is a technique that we're going to be using in several different places. The arc sine, that's what a sine stands for. The arc sine of x means the angle whose sine is x. The angle whose sine is x. Well, if we take the sine of the angle whose sine is x, we're going to get just x back again. So these two things chained together result in just x, but we'll get back to that in a second. Let's just, even if you don't understand what the arc sine means, we can still apply our formula just by rote. Even though we may not know what all the pieces mean, we can still apply our formula. So we say the outer function is sine, so we go cosine. We repeat the inner function. And now I don't know what that derivative is, but let me just write it down in sort of general form. All right, so that's true. The program knows what it is, so it's returning a 1, even though I don't know what it is, or you don't know what it is. We have a true formula, and now we can actually use this formula to determine what the derivative of the arc sine is. The way we do that is we go back to this, and we recall that that thing inside is just a fancy way of saying x. The arc sine, or the sine of the arc sine of x is x. So we're talking about the derivative of x. And we know what that is. That's just 1. So notice the 1 here. That means all of our equalities check out numerically, so probably we're okay. Now I'm just going to put the first and last together. And I'm going to solve for the arc sine of x by just dividing out this term here. All right, and now let me reverse it so we can sort of see it in our focus is now on the derivative of the arc sine of x. So we have a formula for it. Now this formula can be simplified or written in a slightly different form, and we'll get to that eventually. But the big thought here is that if I know the derivative of the sine, I can go through this process and compute the derivative of the arc sine. And that's true for the arc cosine, the arc tan, and as we'll eventually see for log and x, since they're inverses of one another. If we know the derivative of one, we can calculate the derivative of the other. All right, let's look at one other thing, then we'll get back to our proof. And that's this. Now, we haven't yet seen what the derivative of the cosine of x is. We know the derivative of the sine of x, but we don't know the derivative of the cosine of x. And now we're going to use the chain rule to derive that formula. And we're going to do that by first just rewriting this in an equivalent form. Remember, we have a formula relating sine and cosine. This is one of our basic trigonometric identities, and that's going to be sine of pi over 2 plus x. And so these are the same formulas because the cosine of x is equal to this thing here. Remember, this is the one that we have cosine and sine, or maybe it's sine out here on the left and cosine here, and one of those equalities has a minus and one doesn't. This is the one that doesn't. And remember, the way we remembered is the one that does has a minus in front of just sine of x. So here we have cosine of x, so there's no minus there. So this is okay, and the program is telling you that too. We see the 1 down here. If we put a minus in there, we wouldn't see that 1 there. Let's just double check that though, just in case. Now suppose we were to put a minus in there, and then our formula down here is wrong, it's telling us that the program knows you're wrong, so this must be the correct answer. All right, but now we can apply the chain rule to this thing here. What's the outer function? It's sine. The outer function is sine, so this is going to be equal to the cosine, and we just repeat the inner function. And then we differentiate the inner function. What's the derivative of the inner function? It's a constant, that's pi over 2, so that is 0. And x, the derivative of x is just 1, so the derivative of the inner function is 1. But we don't need that 1 there. All right, now we use our basic identity one more time to go the other way. We know that this is somehow related to the sine of x. And notice what happens here. This is the one where we need the minus in front. And now we're okay. So we've shown that the derivative of the cosine of x is minus the sine of x. And we have some idea of where this minus comes from. It comes from the fact that the trigonometric identity requires us to put a minus in front of just sine. And again, back here, if you have cosine of x, the counterpart equality doesn't have a minus in front of it. So now we've got another derivative in our tool bag that we can use when we want. But let's get back to our proof. The proof is very simple now that we've got things all set up. What's the derivative of this composition of two functions, this chaining of two functions? Well, in general, the idea of the derivative is you make a little change back here. You see what change it generates on the other side. You take the ratio, and that's the derivative. So in other words, this is true. If we want to talk about the derivative of the composition, that's equal to the change in z dz as compared to dx. And notice it's close, and I can make it even closer because this side on the right, we have to take the limit. We have to squeeze x down to 0, and that's going to squeeze dy down to 0, and that's going to squeeze dz down to 0. So it's the limit that's the derivative. So let's see what happens as I make h smaller and smaller, or dx smaller and smaller. Same thing. I can get it as close to 1 as I want. There, that's pretty close. All right, but now what do we do? Well, this we're just going to divide by dy and multiply by dy. So that doesn't change anything. And let me group these together. Otherwise the program will just cancel those two terms out, so we don't want that to happen. Okay, so I haven't changed anything. Notice I still have the 1 here. I just divided by dy and multiplied by dy, so it's the same thing. But now I can make these substitutions. dz over dy is f prime of y, and dy over dx is g prime of x. And now I can get rid of my groupers. I don't need those anymore. And finally, I have a y here, a y there, and I want to turn it into g of x, because that's the way I wrote my original formula. So there it is. We're done. That's the proof, and it's certainly, look at the picture one more time. If we want to know how things are changing up here, it's a product of how things are changing from x to y and how things are changing from y to z. So we just multiply those two together and we get the change of z as compared to the change of x. So that is it for the chain rule, and very useful rule it is.